Membrane resistance, membrane capacitance, and cytosolic resistance will, of course, continue to determine conduction speed. Luckily though, we have a really neat trick that drastically decreases membrane capacitance and increases membrane resistance, wrapping the axon in a thick lipid layer, or myelination. Essentially, this means insulating large portions of the axon. Myelinating a portion of the axon largely prevents the efflux, or outflow of ions in that region. Since membrane resistance reflects how easily ions are lost, myelination dramatically increases membrane resistance. Myelin layers tend to be fairly thick, introducing a large separation between the cytoplasm and the extracellular fluid. This significantly decreases capacitance since capacitance is inversely proportional to the distance of charge separation. As a result of these two properties, along any myelinated segment, conduction is extremely rapid. However, in a myelinated region, it is physically impossible to have a working, useful membrane channel. As a result, the charge difference between inside and outside does decay as the depolarization travels along a myelinated portion of the axon. If an axon were myelinated without interruption along its entire length, our depolarization would certainly fizzle out before it reaches the terminal. That's where nodes of Ranvier come in. They're intermittent, very short, unmyelinated regions in which all our usual players, sodium channels, and sodium-potassium A2PAs, are highly abundant. As a depolarization wavefront travels down the axon, it starts in such a region, the initial zone near the axon hillock, and then conducts very quickly along a myelinated portion, decaying a little bit in the process. As the depolarization reaches a node of Ranvier, it again causes voltage-gated sodium channels to open, replenishing the depolarization to full intensity before rapidly conducting down the next myelinated region, towards the next node of Ranvier.